Bismillah ar-Rahman ar-Rahim. Assalamu alaikum everyone. Today's discussion is going to be about validity. Remember, we talked about variables and we talked about the fact that we measure variables using different measures. We talked about the types of measures. Last time we talked about the fact that these measures are not really true measures. They have some error. We talked about the source and the different sources of error that can happen in our measurement, that these errors could be related to the person who is making the measurement, could be due to the instrument, or could be due to the variable that we are measuring. We also talked about how we can overcome these errors and how we can measure the reliability of a measure. We talked about interclass correlation coefficients and how it detects when we calculate test-retest, it detects the correlation and agreement between two measures. And we talked about the fact that the closer the interclass correlation coefficient to 1 is the better reliability. If it is much lower than 1, then the reliability is not excellent for that measure. At the end of last lecture, we talked about the fact that reliability alone is not enough. The variable could be reliable, but it could be measuring something that is different from what I'm intending to measure. And this is validity. And we said that we need to, for the measure to be useful, it needs to be reliable and it needs to be valid. So today we're going to talk about validity. Validity, the definition of validity, as we discussed last time, it is the extent to which a measurement measures what it is intended to measure. In English, simple English, it means, am I really measuring what I'm intending to measure? If I'm after balance, is my instrument really measuring balance? If I want temperature, is my measuring device really measuring temperature, not something else? So measurement validity is asking the question, for example, regarding the thermometer, is the thermometer a valid tool to measure temperature? Is the Berg balance scale a valid tool to measure balance? Which means, is it really measuring balance? Is the thermometer really measuring temperature? If yes, then this measure is valid, which what we need. Let's take a hypothetical. I will show you a target like this one. The center of this target is the true value of the measure. So whatever this measure might be, but the true value is this target. So this is the accurate, precise, true measure of this variable. And the yellow dots are the different times that I measured this variable. So one time it was here, one time it was there, one time here, one time here, one time here, one time here. So what do you see in this? I'm hoping that you see two things. One, that none of these dots, none of these measures came close to the target, which is the true value. The other observation is that every time you measure, you get a value that's different from the other value, and it's all over the place. Okay, so it was not, the measure every time was not close to the consecutive measure, and it was so far away from the center or the target, which is the true value. So this pattern of measurement is not valid because it really didn't come close to the center. it is not reliable because every time I measure, I get a different value that is away from the other value. Okay? Let's consider this scenario. Remember, the true value is in the center. So when I measured, one time I was in the center, close. The other time I was still close to the center. But then some other times I was far away from the center. You see the difference between this one and this one, this one and this one, this one and this one. So I got a scatter, and this is the error. Every time you miss the target, this is an error. So the error is variable. So if I am measuring this error, my margin of error is huge for repeated measures. The same here for repeated measures, the error is huge. So here I was close to the target at some point for a couple or 3 times, but my measurement is still all over the place. So there is some validity. Why? Because I was close to the true value, but very poor reliability because every time I measure, I get a value that is different. It's all over the place. How about this scenario? Well, every time I measure, I am so close to what I measured before. So if this is measurement 1, 2, 3, 4, 5, and so on, they are very close to each other. But what is the problem? The problem is they are all away from the center. So none of this is really close to the true value, which is at the center. Although my repeated measures are very close. So my error, the standard error here, is going to be small for repeated measures, but it is so far away from the center. So in here, you can say what? Is it valid? Is it reliable? Well, it is reliable because the repetition gives you very close number, but definitely not valid because none of the observations or the measurements was in the center. Let's see the last scenario. The last scenario, we find 2 things. That the measurements are close to each other and they are all close to the true value, which is the center. So in this scenario, this measure is valid and reliable. So I hope this illustrates the importance of the 2. Reliability alone is not enough because you are repeating the same measurement, which is far away from the true, although you're getting the same numbers, but you're far away from the true value. And validity is not enough because you need your repeated measures to be close. All right. There are several types of measurement validity. One is called face validity. A second one is called content validity. The third type is called construct validity. And the fourth type is called criterion validity or criterion related validity. We're going to discuss each one alone. However, we are not going to discuss construct validity at this time. All right? So we're going to go over what face validity is, what content validity is, and also discuss criterion related validity. Face validity is simple. It is asking the question, does this instrument appear to be the appropriate choice to measure this variable? Yes or no? So if it is a thermometer, Is it appropriate to measure tension? So the answer is no. But if I'm measuring temperature, then yes, this instrument appears to be measuring what I'm supposed to be measuring, the variable that I'm interested in. Ordinal measures such as surveys, self-report instruments, and qualitative rating scales have some problems with face validity. Why? Because it is very difficult to define precisely the variable of interest. For example, if I'm measuring depression, if I'm measuring balance, if I'm measuring quality of life, if I'm measuring perception of health, all of these things are usually measured in an ordinal scale, 0 to 3, 0 to 5, 0 to whatever. So it is a self-report, and it is very difficult to give a precise definition. What is perception of health? What is that exactly? And how can I ask the question? Is the question precisely asking about this? So that sometimes creates a gray area in the face validity. I give you an example here. If someone is evaluating an employee as, so this is the scale, does not meet expectations, meets expectations, exceeds expectations. Do you see a problem in this? If you are working for someone and someone is evaluating your work, and the evaluation form does not meet expectation, meets expectation, exceeds expectation, I'm sure you can see that expectations are not usually very clear to the employee, and sometimes the employer has different expectations. So really the precise definition of the variable is not there, and the difference between exceeds and meets are, again, the area between the two is really clear to the employee and to the employer. Content validity, on the other hand, is asking if the instrument represents all the relevant facets of the intended variable. So if you have a variable that has different dimensions, different facets, different levels of or different domains, is this instrument able to capture the change in all these facets? Also, it should not contain unrelated measures to the variable of interest. So if I'm asking about depression, I should not have questions about other measures than depression. If I'm asking about health, I should not be asking questions about something else. So the instrument, to have content validity, should have all aspects of the variable of interest and should not have anything other than the variable of interest. It's usually pertinent to multidimensional measurement. Of course, when you say all facets, so it means that it has several facets or several dimensions, which is really very common in many instruments. If you have a disability measures, if you have functional measures, self-report tools, all of these things have different dimensions. For example, if you look at the Berg-Balance scale, if you look at the dynamic gait index, all of these instruments, which has different items, you're hoping that each item is related to the variable of interest. For example, for the Berg-Balance scale would be balance, and it should not have test something that is not related to balance. This is an example. A balance test should include activities that challenge an individual's ability to maintain an upright position, but it should not include activities that require the subject to maintain a supine position, because in supine, you are not really challenged, or balance is not challenged. Content validity also is trying to determine, or important to determine, because there is no external standard or statistical criterion against which an instrument can be judged, or it is so it is subjective. What does this mean in simple words? It means that you say that, for example, the Berg balance scale is measuring balance. Is there a gold standard that measures balance that I can compare the Berg to and say, well, I came up with the same score? Actually, there isn't. And this is a problem, because if you have a gold standard, for example, if I say the bone mineral density, or DEXA, which is the gold standard for measuring bone mineral density, if another instrument or another equipment is invented, I can always compare my results to the DEXA. Why? Because DEXA is the gold standard. In many of the tools that we use and instruments that we use, we don't have a gold standard to compare to. So content validity is a little bit subjective. And I'm saying a little bit subjective, not totally subjective, because usually we get experts to decide if the content validity is okay with this instrument. So the usual method for establishing content validity is to assemble a group of experts whose knowledge is deemed to be extensive enough to identify all of the types of activities or items an instrument should represent. Let me say it again. If I came up, for example, if I invented a test to measure whatever, let's say balance again, and I measured, I have an instrument or a test that has 15 items. And I'll measure the person's walking, the person picking up something from the floor, the person jumping up and down, whatever. So, as I said, there is no gold standard for balance. So I need experts, people who are researchers in the area, experts in the area. They look at the items, the 15 items that I came up with, and they can tell if these items are related to balance, if I have any of the items that are really not measuring balance. And that's the way we decide on these tests. So again, it is subjective, but the subjectivity is eliminated mainly by the opinion of experts. This is, for example, the McGill pain scale or questionnaire. And this questionnaire was compared to the visual analog scale that I'm sure you all know. And they found that this McGill questionnaire has more content validity as a pain measurement than the visual analog scale. If you look at this instrument or this measures, you will see that it is asking the person about a lot of things about the pain. It's asking the person, where is your pain? And the person would put the place of the pain. It is asking, what does your pain feel like? So is it pinching? Is it dull? Is it tightness and so on. So that's another section. How does your pain change with time? And how strong is your pain? So it's asking about a lot of aspects of the pain. On the visual analog scale, it's asking mainly about the severity of the pain. But in here, it's asking about several aspects. Remember, the content validity is asking if the instrument is covering all the facets, all the dimensions of the variable. So this study showed that this instrument is better in content validity than the visual analog scale, which makes a lot of sense when you look at the form. Criterion validity, on the other hand, which is another type of validity, it reflects the degree to which the score are related to scores obtained with a reference standard or a reference criterion, or again the gold standard instrument. So criterion validity is comparing an instrument that is considered the gold standard and how the new instrument is relating to that gold standard. And we have two types of criterion validity. One is called concurrent, and concurrent, from the name, we're talking about two things that are happening at the same time. The definition of concurrent validity: when the measurement to be validated and the criterion measure are taken are relatively the same time, which means concurrently, so that they both represent the same incident of behavior. In English, it means that you have two things, and these two things are measured, these two things measure your variable. One is considered the gold standard, and the other one is not the gold standard. So you measure the same person, the same phenomenon on the same person at the same time using both instruments. For example, goniometric measurement. If I am using the goniometer to measure knee angle, for example, at the same time I'm taking an X-ray radiograph of the joint angle. Of course, the radiograph is the gold standard. You're looking at the femur and the tibia, and you're measuring from the angle between the femur and the tibia, if we're talking about the knee, right? So that's the gold standard. Am I able to get the same results if I have the person, if I measure on the actual person with his muscles and skin and fat and everything? Would I get the same number? So many studies have looked at this, at measuring with the goniometer and measuring on the radiograph at the same time, and they validated really the measurement with the goniometer, and they were very close, and you will find these studies. There is another type of criterion-related validity, which is predictive validity. Predictive validity, from the name, we're trying to predict something that's going to happen in the future, right? So the definition that it is a measure that is a predictor of some future event or criterion score. To determine that a tool has predictive validity, a test is performed, and over time the criterion is examined. For example, if I test a person for balance, or for example the functional gait assessment, which is a test for functional gait, can I, from the score that the patient gets on this test, can I say if this person is going to fall in the next 6 months? And actually we have many instruments that can do that. We have the Berg-Band scale, we have the dynamic gait index, the functional gait assessment, the Fullerton advanced balance scale. All of these scales have cutoff score. They tell you if the patient scored less than this number, then this patient is at high risk for falls. So you expect this patient to fall in the next 6 months or the next year. So this predictive validity is important so we can decide for patients if they are going to have that future criterion or future event from the score that I'm getting today. Another important thing that a measure must have, which is responsiveness to change. Is my measure able to change if the patient or the phenomenon is changing? If I have a thermometer that I put in outside of my home and the thermometer is not very sensitive and I feel it's very hot and I look at the thermometer and it is not really moving precisely as much as the increase in the temperature. So responsiveness to change is the ability of the instrument that can reflect the change even if the change is small. So we definitely need instruments that are reliable. We talked about that. Valid. We talked about that. But also able to detect change in the phenomenon or the variable of interest, whatever it might be. Responsiveness to change depends on several factors. One, the fit between the instrument and the operational definition of the phenomenon of interest, and I will talk more about this. The number of values on the instrument scale, which means is it in millimeter, is it in centimeter, is it in kilograms, in milligrams, in ounces? That's the number of values. The standard error of measurement associated with the instrument. And the standard error of measurement, remember the target, when you had the dots all over the place, that's a huge standard error of measurement. But when the dots were very close to each other, that's a small standard error of measurement. So responsiveness to change again. The first criteria, we said the fit between the instrument and the operational definition of the phenomenon of interest. It talks about really what we just explained, the construct validity. The measure should match the operational definition of the phenomenon of interest. For example, if joint position is the construct of interest, then the appropriate instrument should be a goniometer, not a strain gauge. So we're talking about is the tool fit to measure what we need to measure. So that's easy to understand. The number of values on the instrument scale. The more values on the scale of the instrument, the greater the opportunity to detect change when it occurs. A tape measurement, for example, we use tape measurement to measure wounds. So a pressure ulcer or a bed sore or a bed wound, we measure it with a tape measurement. If the tape measurement is marked in millimeters, it will be more responsiveness to change. It will detect the responsiveness or the change in the dimension of a wound than a tape measure marked in quarter or fraction of an inch. So when the measure is more precise, when the units are smaller, then I am more apt to capture change than if the units are away from each other. Right? So if I'm buying anything in kilograms and I put what I bought on a scale, digital scale, that can give me 1.1 of a kilogram, then I am able to detect the small differences between the measurement than if I am measuring it with the scale that the uh, uh, sellers use, which is really you put an apple and then it goes down, you take the apple out, you get another apple, and then to try to balance the scale. Of course, if you put this on a digital scale that has decimal points, you probably bought more than a kilo or less than a kilo by a fraction, because the scale that you used was not precise enough to detect that difference. Also, the standard error of measurement associated with the instrument is the extent to which an observed score are dispersed. Dispersed means scattered, متبعترة متنطورة around the true score. كل ما كانت مبعترة away from the true score, كل ما كان the standard error of measurement is bigger. So it makes sense that an instrument with a large standard error of measurement will be less responsive to change, because the true value are lost in the inaccuracies produced each time a measure is repeated. So a good instrument should have a small standard error of measurement. Okay? Another important factor in measurements and in measures is the minimal detectable difference or the minimal detectable change. So minimal detectable difference or minimal detectable, also known as minimal detectable change, is a concept that is important in measures. What is it? It is the amount of change in a variable that must be achieved to reflect a true difference. Let me give you an example. If I am measuring, let's stick to range of motion of the knee, which is easy to understand. And I had a patient who had a knee condition, whatever it might be, and I measured the range of motion of the knee to be 35. Okay? The patient received physical therapy for 2 weeks. I measured again, and now the knee range of motion is 37. So it increased by 2 degrees. Is this a true difference? Is this a reflection of improvement of the knee range of motion of this person? I need to know, to answer that question, I need to know the minimal detectable change that I must have to say that these 2 degrees are actual true difference, or it is just within measurement error. So to be able to answer that question, I need to know the standard error of the measurement. If the difference is more than the standard error of the measurement, then it is a true change. If the 2 degrees are within the standard error of measurement, then this is not a true difference. This is what this is saying. It is the amount of change that just exceeds more than the standard error of measurement of an instrument. The greater the reliability of the measure, the smaller the minimal detectable change. Again, if the measure is all over the place, scattered all over the place, then the standard error of the measurement is huge. Then the minimal detectable change is going to be huge. If the measure is very reliable, the standard error of measurement is very small, then the minimal detectable change would be small. So two important values are used to calculate the minimal detectable change for every single variable. So the minimal detectable change for flexion of the elbow is different than extension of the elbow, is different than internal rotation of the shoulder, extension of the hip, and so on. So the standard error of the measurement must be calculated, and then the interclass correlation coefficient then is calculated, and from there we can find the minimal detectable change. These are studies that were done to detect or to decide the minimal detectable change for horizontal adduction of the shoulder. That's the only joint that has horizontal adduction. So for horizontal adduction of the shoulder, according to these authors, in a paper that's published 2010, they found that the intra-rater reliability, again, what is intra-rater? Same person measuring several times. The ICC was 0.96. Remember, the closer to 1, the better the reliability. So this is excellent reliability. The inter-rater reliability, this is when 2 or 3 people are measuring the same thing, is 0.90, which is excellent. The standard error of measurement was 4 degrees when measured by several people, and the minimal detectable change was 9 degrees. What does this mean in English? It means that if you have a patient and you improved the horizontal adduction of this patient by 3 degrees, 3 degrees is less than 4 degrees. So this is still within the standard error of measurement. So this is not considered a true change. So there is no change in the condition of this patient. But if you have made a difference of 7 degrees, now 7 degrees is not within the standard error of the measurement. However, 7 degrees is less than the minimum detectable change. So again, 7 degrees is not enough to say that the patient is better. What is the minimum that I need? I need 9 degrees to be able to say that the patient is improving. Okay? This is another study that was published earlier about shoulder related to shoulder external rotation. The intra-rater reliability was 0.93, which is excellent. Inter-rater reliability, the ICC was 0.8, which is not too bad, but not as good as the intra-rater. The standard error of measurement is 4.9 degrees. And the minimal detectable change was 7 degrees. So to be able to say that you have made an improvement in the shoulder external rotation of this patient, you need at least 7 degrees, which is the minimal detectable change of shoulder external rotation. I hope these examples made it clear how you look at the minimal detectable change. Another important concept in measurement is the floor and ceiling effect. Floor and ceiling effect talks about a test or instrument that is either too difficult or too easy. So floor and ceiling effects occur when the scale of the measure does not register a future decrease or increase in scores for the lowest or highest scoring individuals. It simply means that when I measure the patient is scoring either the highest score or the lowest score. But then if the patient improves or the patients deteriorate, the scale is done. I don't have any more scores to put. For example, a floor effect, if you are dealing with a disability index for a patient with a progressive disorder. For example, patient has Duchenne muscular dystrophy. The patient is getting worse. And when you tested the patient scored the lowest score on the scale. But you know that this patient is going to get worse. But you already scored the lowest on the scale. You don't have any more scores. However, the patient is deteriorating more. So this is a floor effect. So this scale is not suitable for this patient because this patient can get to a point that is not on the scale. The ceiling effect is just the opposite. If the patient, again, on the same scale, a patient had the highest score, while it is anticipated that he will improve. For example, for the let's say the Fullerton Advanced Balance Scale of balance. Now, if the patient scores 40 out of 40, and then the patient is treated, took like a couple of weeks of physical therapy, and the patient improved, how can you record the improvement? The patient already scored 40 out of 40. So even if the patient improved, you can't really record that improvement because you have reached the ceiling SAF scale. Floor and ceiling effects can be avoided with a thorough operational definition of the phenomenon to be measured and careful construction of the measurement instrument. So that's why you need to be careful when you choose an instrument. For example, if I have a patient who is at a low level of function, maybe the Berg balance scale is good for that patient. But then it could be too easy for patients who are community dwelling, meaning they are out and about, they're driving their cars, they're going to the market and so on. They have problems with balance, but then when I test them with the Berg balance scale, they score the highest score. But when I work with them, I'm not going to be able to show their improvement because they already got the highest mark on that scale. So again, the floor effect is failure of a measure to detect lower scores for patients whose status has declined. The ceiling effect, failure of a measure to detect higher scores for patients whose status has improved. So these are very important characteristics of measures that when you read the literature, when you read the evidence, you need to pay attention to these things. A measure is not useful if it is not reliable, if it is not valid, if it is not responsive to change. If I don't know the minimal detectable change, then my assumptions and my conclusions are not accurate. And I need to pay attention to the instrument that I'm using with the patient so I don't get stuck with a floor effect or a ceiling effect. Okay? I hope this was clear. Good luck to you and have a good week. Assalamu alaikum.